Hi, I'm Bob. Welcome back to 5-Minute Econometrics, a program focusing on fundamental concepts and estimation methods. Today, we will distinguish between two concepts: perfect collinearity and multicollinearity. We have encountered these two different but related problems when regressing a model. Recall that one of the classical linear model assumptions is the no perfect collinearity assumption. It states that there should be no perfect collinearity or perfect linear relationships between explanatory variables. Otherwise, we cannot estimate the coefficients in the model. We can clearly see it using the matrix form of the OLS estimator. If there is a perfect linear relation between some explanatory variables, then the X transpose times X is not a full-rank square matrix, and therefore it is not invertible. Since its inverse matrix does not exist, we cannot obtain the OLS estimator beta hat. The no perfect collinearity assumption is also called the full-rank assumption. The explanatory variables matrix X should have a full column rank. In a regression with k explanatory variables and n observations, matrix X should have a column rank of k plus 1. It happens when there is no perfect collinearity or perfect linear combination between explanatory variables. In other words, perfect collinearity leads to a failure of OLS estimation. Multicollinearity, on the other hand, is not a violation of the OLS assumptions. We can still compute the OLS estimators in the presence of a multicollinearity problem. Multicollinearity means high but not perfect correlation between two or more explanatory variables in the model. Multicollinearity often results in insignificant OLS estimates. We have discussed it in the previous topic. Let's have a brief review. The t-statistic of the OLS coefficient estimate beta j hat equals the estimate divided by its standard error. The standard error can be estimated by the square root of the variance of the estimate. The variance equals the error variance, sigma square, divided by the sample variation in xj, SSTJ, and 1 minus rj squared, where rj squared is the r squared from regressing xj on all other explanatory variables in the model. If xj is highly correlated with other explanatory variables, rj squared would be close to 1. It leads to a large variance, which eventually results in a small t-statistic and statistical insignificance of xj. The multicollinearity problem can be alleviated by using more observations. In that case, the sample variation in xj will increase, which helps to reduce the variance and offset the effect of multicollinearity. An extreme case of multicollinearity is perfect collinearity, in which rj squared approaches 1. Today, we have compared perfect collinearity to multicollinearity. No perfect collinearity is one of the Gauss-Markov assumptions that makes sure the OLS estimates can be obtained. While multicollinearity is a problem that could cause statistically insignificant estimate. Perfect collinearity is an issue we should always avoid. But multicollinearity, or correlation between explanatory variables to some extent, is inevitable in most regression models. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.